and it's very useful and very important for those of you guys working with natural fractured rocks, because your natural fractures are going to be oriented at some given orientation. You may have one set, two sets, and how those orient with respect to the in situ state of the stress is going to tell you a lot about what's going to happen when you change the stresses around those fractures. All right, so in order to solve this problem, what we're going to do is something similar to this, and let's complete this by saying that this one was sigma 2 and this one was sigma 1, but now instead of having a triangle in 2 dimensions, we're going to have a I always forget how this one is called. Should be, is it a tetrahedron? Looks like a pyramid. It's an element that is composed with sides which are 4 triangles. That should be tetrahedron, right? I don't know. I don't forget. It doesn't matter.
Yeah.
Is it tetrahedron?
Yeah.
All right. So with this volume, which apparently is called a tetrahedron, we're going to do the same thing that we did before. But now in this volume, we're going to apply stresses in 3 dimensions. So normal to face number 1, which is this one, perpendicular to axis number 1, if I want to do the summation of forces in direction 1 equal to 0, what is going to be the stress acting on this side, on face number 1, in direction 1? It's going to be sigma 1, 1. There is also sigma 1, 2 and sigma 1, 3, but I don't care about that because I'm just doing equilibrium now in direction 1. On face number 2, which is this face over here, in direction 1, which stress do I have? Sigma 2, 1. Again, there are some other stresses, but I don't care about them right now because I'm just looking for the ones in direction number 1. And in the same way, here, I'm going to have sigma 3, 1. All right? Well, these are stresses. These are not forces. So if I want to make the equilibrium, I need to multiply them times their respective areas. So for example, this face over here is going to have an area A1. Face number 2 is going to have an area A2. And face number 3 is going to have an area A3. And the area which is going from the plane that goes from 1, 2, and 3. So imagine a plane that is cutting through 1, 2, and 3, which is going to be a plane like this, which will be the side that you are directly seeing on this tetrahedron. This one is going to have an area which we're going to call A. And on that side, there is going to be in the center, a stress that we're going to call T. And that T is going to be a vector. Here you cannot see very well the orientation, but it's going to have components in several orientations. One of them, which is going to be in direction 1, and it's going to be T1. So when I write the equilibrium equations, I will have that sigma 1, 1 times area 1 plus sigma 2-1 times the area 2 plus sigma 3-1 times the area 3 has to be equal to the component T1 of this vector T times the area A.
What's T again?
T is the components of the stress that we're going to calculate, from which we're going to get sigma n and tau. It's the same as sigma n and tau, but now I just made it just one vector, because in 3 dimensions it's going to be a little more difficult to separate it. So for now, let's just assume it as 1, and it has a component in direction 1, which is T1. All right, this is going to be our equation number 1. Let's see our set of equation number 2. And in order to do that, we're going to use some geometry. What is the volume of this tetrahedron? Anyone remembers how to calculate the volume of these things?
Side, height, right?
That would be of a triangle, right? But now this is a volume, but it's very similar. It's 1/3 of the area times the height, where the height is the length perpendicular to the area till the highest point. For example, if I draw this thing, this tetrahedron again, and we said this is the area A, let's say that the distance from here, this is a point on the area A, and it goes through that point. This is going to be H. And the same way, I can do this for the other faces. I can also use the area A1 and multiply times the distance that goes, if I use A1, it will be the distance from here to there. And so I'm going to use this is 1, this is 2, this is 3. That will be the distance OA, is going to be the distance OB, and the distance OC from here to there. So this is going to be A1 times the distance OA. And since these two are exactly the same volumes, I can find a relationship that tells me what is each of these areas as a function of the angles from this line to each of the elements of the base. So let me first write the equation, and then I'll show you the physical meaning. So A1 is going to be H divided OA times A. And what is H divided OA? So this is H. Remember, this is the point on the surface A, and this is OA. Let's do it first. It's easier. Let's do it with B. What would be H divided OB? Can you see that that's going to be the cosine? Well, this is going to be the angle, not the cosine. But this is going to be the angle BOC. And the ratio, in this case, of H divided OB is going to be the cosine of the angle BOC.
I don't think it's BOC. You have not defined the.
I'm sorry, BO.
You have to define the point.
That's the point, let's call it N. Is the angle BON. Thank you for that. Yeah. Is the angle BON. And in the same way, this thing is going to be equal to the cosine of the angle, in this case, AON. And A2 is going to be the cosine of BON, and A3 is going to be the cosine of CON. And each of these angles are going to be what are called the cosine directors of the vector n, which I'm going to define right now. N is going to be a vector which is perpendicular to the area A. And in general, I can say that A is going to be equal to each of these A's, 1, 2, or 3, is going to be equal to the component of the vector n, because n is going to have the magnitude of n is going to be equal to 1. So directly the component of each of those is just the cosine of that. And so this is going to be each component times the area. Where complete this, n is perpendicular to the area A, and let's move this down a little bit. And is N2, N1, N2, N3, with each of those components are the magnitude in direction 1, direction 2, direction 3. So for example, if the vector n is pointing exactly in direction 1, the cosine of 0 is 1, and this will be number 1. The other two will be 90, so cosine of 90, 0, cosine of 90, 0, n is 1, 0, 0. And if you have something which is not aligned with any of these axes, then you're going to have 3 elements in each position. Okay, so we're very close. Very close.
Can you move it down
Yes.
just a little bit? Oh, the other way. Yeah, just those end things. Thanks.
We're very close. The only thing that we have to do now is to use this new equation that we just found on the equation of equilibrium. And this is going to tell me that, is that good? This is going to tell me that sigma 1, 1, I know what A1 is now, is N1 times A, and sigma 2, 1, A2 is N2A, sigma 3, 1 is N3A, and this is equal to T1A, but as you can see, we have A's everywhere, so we're going to cancel those A's, and the final result is that this T is just a combination of multiplying the stress tensor elements times the cosine directors. And we can generalize this and say that the elements T1, T2, and T3 are going to be a product of the stress tensor times the cosine directors of the vector n. The vector n, we're going to see later on, that has a very specific physical meaning, and it depends on the type and on the dip and strike of, for example, a fracture. And basically, this is the final equation. We know what is the state of stress in a given location. We know what is a vector n, which depends on the orientation of a given plane in 3 dimensions, given by the cosine director of a vector perpendicular to that plane. And this equation tells me that this vector t of the components of the stresses is just equal to t is a vector, just one line, the stress tensor times the vector n, which is exactly the same thing I wrote here, but in a more compact notation. And this is the last step. If I want to compute what is the effective normal stress, I need to multiply T one more time times n with the dot product. So usually T and n are not going to coincide. So let me come back over here. We have the T. This is n, always perpendicular to the plane that we chose, but T